uniform circular motion, or as I like to call it, how to accelerate without really trying, because you're going to see it's a different kind of acceleration. Really, it's just motion in a circle. You can imagine some mass moving around the circle at a constant speed. So let's describe it with some bullets, this being hexes and everything. So first of all, one property is that the velocity is along the path. Or you might want to sound fancy and say it is tangential to the path. But really that just means the velocity vector, wherever you go, is along the path like this. If it's going around that way. Always along, tangential to the path. The second bullet is you have constant speed. Okay? The speed is the magnitude of the velocity. So even though we're going around, it's keeping the same magnitude of that vector. So you might say if it's constant speed, it's not accelerating. But, there's a big but, the change in direction, change in the velocity direction counts as acceleration. Okay? So remember, acceleration, what is acceleration? It is the change in velocity over the change in time. The change in the velocity vector. The velocity vector is changing as it goes around this circle. We could do a quick analysis of it. We can imagine the mass is here and the mass is here. The velocity is that way and the velocity is that way. Let's think about what is delta v in that case. Well, delta v would have to add the vectors. That's v final. We'll say if this is v final, v final minus v initial. And we imagine, what would that subtraction look like? It would be final minus initial. So it would be final vector, and then you add the negative of the initial vector, right? So the initial vector would be like this, head to tail, if you added it, but you're going to subtract it, so you make it go the other way, right? Let's see, so it's there, head to tail would be like that, but we make it go this way, so there's kind of v initial. There's negative v initial. So that's what you get, there's delta v. And you divide it by a scalar delta t, and you find that that is the acceleration. In this case, that'd be the average acceleration. So what you see is the acceleration points inward, like that. And that's why it's called the centripetal acceleration. Accel points inward. And that's what we call it AC, the vector AC. So one property of uniform circular motion is that the acceleration is perpendicular to the velocity at all times. As you go around the circle, the velocity is always tangential or along the path, and as you go around the circle, the acceleration is always perpendicular to the path. So A and V are always perpendicular to each other. And then I guess the last thing you need is the magnitude of the centripetal acceleration. The direction is this complicated thing that turns the whole time. If you wanted the magnitude, it's equal to the speed squared over the radius of the circle. So here I've drawn this thing in the way. Let me erase my little vector diagram here. But if I now draw here in the center of the circle like that and say that's the radius, a little r, then at all times the centripetal acceleration has the value v squared over r.